Thank you. Thank you very much for the invite to come and talk about HISPEC. I have the privilege and the honor to present the preliminary design of the HISPEC instrument. I also have the burden of condensing 400 PDR slides into 15 minutes. So let's try and do it. I'd like to start off by acknowledging the entire team. It's a cross-institutional collaboration amongst many scientists who've all contributed to what I'm about to show you. And here's a photo close to the end of PDR last week with our reviewers. And I'm happy to report that we successfully passed preliminary design last week. I only have one slide on science, and this overlaps with previous talks. This is a simulated population of planets based on Kepler occurrence rates, showing the breadth of the science that HISPEC will be able to do. It's not just a PRV machine. We're going to use the fact that it's a diffraction limited AO-fed instrument to be able to spatially resolve and spectrally characterize exoplanets, as CAPIC is doing currently. Closer in, we should be able to support transit spectroscopy. It's a science case that Bjorn Benneke is leading. And of course, the PRV will allow us to detect planets, but also help constrain masses. One unique mode that I'll mention later on is that HISPEC is going to have access to a nulling mode, which gives us the ability to get closer in than imaging, but characterizing higher mass objects. Oh, I should point out, I encourage you to go see Dimitri Marway and Caitlin Horstman's posters who will tell you more about the science case. So HISPEC occupies a pretty unique parameter space. This is a Venn diagram put together by Dimitri that shows the size of the telescope, the resolution, the diffraction, the fact that it's operating at the diffraction limit and its YJHK in a single shot. And HISPEC is really the only instrument that will occupy all that parameter space. It's driven by all the science cases I pointed out, with the resolving power primarily being driven upwards by transit spectroscopy. The sampling is driven by PRV, the stability also by PRV, and because of the fact it's on a 10-meter telescope, it's really trying to push to 15th magnitude sensitivity. This is a nice plot put together by Sam, adapted by Dimitri and Ashley, showing the relative landscape based on wavelength coverage. And HISPEC and Spiru have very similar wavelength coverage, where HISPEC has the advantage of being on a larger telescope. And this will complement KPF. So the instrument overview up here, given that it is diffraction limited, we use single mode fibers, we need an adaptive optics system to feed the light. And this is on the NASA platform at Keck. The telescope is missing here, just for clarity. And the light, I realize that has two meanings. The light runs through the fiber out through the building, follows a path very similar to KPF into the crypt, into the basement, where HISPEC will be located with two of its dewars. And for reference, KPF will be down the corridor. So the front end instrument, obviously coupling into single mode fibers is rather challenging. Jonathan talked about that today. This is effectively being mastered as well at Keck. We have the Keck Planet Imager and Characterizer, which has successfully been operating for 3 years right now. And so HISPEC will borrow a lot of heritage from that. When the light is about to exit the bench, after being corrected by the AO system, it's fed into the front end instrument, which is a compact tool for aligning the light or the target with the fiber. We do no internal AO correction at this point. It's just meant to inject the light efficiently. And for reference, a future KPF injection unit might appear here. So this is the optical layout. It's rather simple. All we have is a collimating OAP, an atmospheric dispersion corrector, a field steering mirror, which is in a pupil plane that allows us to steer the light onto the tip of the fiber. And otherwise, it's a collimated beam space with a final focusing lens used to optimize the F number for coupling. Because single mode fibers you can't efficiently get a single mode fiber that spans YJK in a single shot. We had to split this into 2 fibers. And it turns out if you get really greedy with wavelength and resolution, there are not enough pixels on a single H4RG either. So we need 2 of them. So it just makes sense to split the light here at this point, and it stays separate from this point. So we have replica here. We have a HK injection and a YJ, and they're just replicas of one another. The nulling mode, I wanted to say a bit more about. At the mask selector mechanism here, we insert a vortex mask, and this combined with a single mode fiber enables vortex fiber nulling. This plot here is showing you what the coupling map to a single mode fiber looks like when you inject a vortex spiral phase into that mode. And you see at the center of this, it's dark, which means starlight doesn't get into the fiber, assuming no wavefront error and no atmospheric dispersion. Of course, we simulate those. And this light ring tells you the transmission profile of the system. And you can see here in a cross section, it peaks at about 1 lambda on D at about 20%, which means if an object is within 1 lambda on D of your star, even if you can't see it, 20% of its light's going to get into that fiber. You can take a spectrum and you can separate it in the spectral domain. And this is being tested on CAPIC at the moment, and I encourage you to go see these papers for more details. Of course, with any acquisition system, you need a tracking camera. In our case, that's the H2RG. Even though we're on a 10-meter telescope, if you want to push to 15th mag, you're going to need to have sensitive detector. So we don't use a lot of the pixels, and this is a JWST loaner, and we're combining it with an Archons controller and trying to use guide window mode to get the sensitivity and speed. One other innovative feature of HISPEC, given the fact that we're trying to do YJHK in a single shot, we're trying to not interrupt the science light to do this. And so Ashley Baker and our team suggested, why not try to do tracking in the JH gap, which could be a scary proposition, but this slide is just trying to convince you that we've looked into the issues to do with that. On the right here, we're showing you data from an integral field spectrograph taken on sky at Subaru, showing the correlation between the astrometry in the J, H, and JH gap bands. And these linear correlations tell you that when a spot moves in the J band, it moves equally in the JH gap, so you can use them as a proxy for predicting motion. Anyway, I can talk more about that, but I won't for now. Another innovative technology we use on HISPEC are these beam shaping optics. So to couple efficiently into a single mode fiber, you need a flat wavefront. Jonathan talked about that. The other thing you ideally do is better match the telescope beam to the quasi-Gaussian nature of a fiber. And these beam shaping optics do exactly that. And when you achieve this, effectively you can increase the 65% theoretical efficiency of Keck up to about 85%. Right, the fiber system, we use 2 fibers, a silica fiber in the visible, that's a commercial grade fiber, which is actually the fiber that IRD uses. And in the HK channel, we have to make a custom fiber with Zeblan with a company called Louva Fleuret, who also made Spiru's fiber. And we have similar specifications to Spiru, except that we're single mode. So this is a development. For a high efficiency or a high throughput mode in the regime where you're down towards 15th magnitude, and in the blue, your Strel is really starting to tank, we have this innovative component called a photonic lantern. Effectively, this has a multi-mode input. So in this case, it's supporting 3 LP modes that get split into 3 single mode outputs. I am happy to explain how these things work in more detail, but effectively there's no free lunch, in that instead of having a single trace on a spectrograph, you now have 3 traces. So you occupy more pixels to do this, but it gives you a get out of jail free card to collect some more light at the faint limit. And this is a device that they built a few weeks ago for us and are currently characterizing. So the fiber routing is rather complicated. I'm only showing the blue channel here. At the input in the injection unit, the blue channel will have 2 fibers, the lantern I just mentioned, and also a single mode system where you can inject light from a target, speckles, and a background into the input. This is then routed through the building with long fibers. It hits a mechanical switch, which allows us to reconfigure which of these beams is sent to the spectrograph slit, as we only have 3 fibers on the slit. And then up here in the calibration system, we have a bunch of calibration sources I'll mention that can be selected from another switch that then routes the light to this one and into the slit. Here is what the mechanical switches look like. These are physical switches. They actually have SC connectors, so they can pull the cable back, translate, and then reconnect. So it's a latching, delatching mechanism. It works pretty well. And I encourage you to go see Aoi Takahashi's poster on both the progress with our switch testing and also connector losses. We need 6 total switches, and here are all the states of those switches to make HISPEC work. The top 2 are the main science switches. These are the ones that select what goes to the slit. And the bottom ones are much simpler. These ones are selecting the calibration source and where it has to end up. And so with these, you can come up with different combinations. So in this case, you can send science background Cal, science speckle background Cal photonic lantern to the slit. So you can reconfigure the system as you see fit. I will say people that are used to working with multi-mode systems might be freaking out at this point. But with a single mode system, the nice thing is that it doesn't matter what I do to the input, the output is spatially invariant and temporally invariant. The only thing that happens is the intensity goes up and down, and also what Rose just said about polarization. So here's just one quick example of how this could be configured. You might send the laser frequency comb to the main switch. From that point, you'll say, well, I want to calibrate the entire slit. So we have to split that light 3 ways and send it to the slit. So this is just one quick example. Calibration sources, all the usual suspects. We'll also have integrating spheres inside the spectrograph to flat field the detector. We will be able to get flat fields from that. We'll feed the light through with a fiber. We have gas cells and hollow cathode lamps for spectral calibration for absolute, and then etalons and laser frequency combs for relative. We take benefit from 2 previous projects in terms of laser frequency combs, in that KPF is paid for a Menlo comb, and we are tapping the infrared light thanks to their generosity. And there is also a HK EO comb being developed by Stephanie Leifer that will be delivered this year and will be operational by the end of the year. So they arrive 3 years before we do. We have some backup etalons in the red and blue channels built by Stable Laser Systems. Building on a lot of heritage from their developments with PAVI, NUID, and HPF. And finally, the spectrograph, I won't say a lot here. The optical design is, as Rose pointed out, is all reflective, which was prompted by trying to remove these polarization effects. We have a slit here. We use a TMA for a collimator and a camera. This follows the design principles of iLocator. We have an Eschel grading here, which is actually going to be a Canon germanium grading, sorry. And this is direct ruled. I encourage you to go see Takayuki Kotani's poster, who will tell you all about the grading development, the RCWA, and the cryogenic test facilities we have to test this. And there's also a reflective cross disperser. The 2 spectrographs are near identical. The detector in the red channel is a H4RG15, and in the blue is a H4RG10. The sampling is about above 3 pixels in most of the red and blue channels, hitting about R of 140,000, about 90,000 in the blue and red respectively. This is showing you the efficiency of the components and the total roll-up. And here, this spectrum, I want to point out, is from RCWA, which took months of work by Canon. And from what we've seen, they typically make their gradings to within a few % of what you see on these diagrams. So it's very impressive. Second last slide. This is the optomechanical layout at the moment. What you're seeing is an optical bench. You're seeing subplates for each of the different collimator camera and gratings, and all the mechanical mounting will be made from Invar. And this is the final thing with the shell. So you see here, there's a cold shield. There's the cryostat wall. There'll be an MLI layer. There'll be baffling. All that's yet to be detailed out. I'm not going to talk at all about the performance and error budgets. Ashley Baker has done a fantastic job of tracking this for this instrument. So I encourage you to go see her poster where she can give you more info. So with that, I thank you for your time. Encourage you to go see these posters. And I just want to say that now that we moved into the DD phase, we are hiring both at Caltech, UCLA, and UCSD for any and all of these roles. So if you're interested, come see me or any one of the people on these posters. Thank you.
Thank you. It's impressive how much new technology you're using here. So what's the timeline, by the way?
Well, at the moment, the first science is end of 2026. So
okay, thank you. One question. Time for one question. Personally, I have a lot of them, but okay, what?
Great talk, Nem, and very exciting stuff. I'm just curious about your 3-port photonic lantern. So do you have, I think you have to collapse all of that light into one spectrum for it to really look like what you're looking at, right? It's not like you get 3 independent spectra that are all the same. The wavelengths can go in random places, right?
That's right, that's right. So if you were to look at them in the spectral dimension, you don't get an even split across the 3 traces. It depends on what the AO is doing, what the injection is, because it's traumatic coupling terms. So you will get some wavelength profile across the 3 of them. And then you need to, RSS the channels at the end once you've done your cross correlation or whatever you're doing to build the signal back up. Ashley Baker actually did the analysis on taking that lantern, putting it through the simulation, and then looking at how to extract that data. So I encourage you to talk to her about the specifics of how she did it.
Thank you.
Okay, thank you, Nemanja, again. And